So finishing up with logarithms. Obviously, we've been talking about logarithms. Okay. We have also talked about the common logarithm. How do you recognize a common logarithm? Got a certain base. What's that? No, it's got a certain base. 10. Yes. Okay. There's another special type of logarithm called the natural, where its base is a constant number, is a number that never ends or never repeats, otherwise similar to pi, which is an irrational number. And it is a special number because it represents continuous growth and continuous decay. And this number we refer to as the letter E. And like I said, it is a decimal number that never repeats or never ends, which means we call it an irrational number. And you can see at the bottom of the page the approximate value of E. It's 2.718 or 2.72. Okay? It's not a variable, it's a number. And here's how we get it. Okay? So just to show you where it comes from, and a good way to show you is that at the beginning of this lesson, we used that compound interest formula where we calculated the value of an investment after so many years. And remember, I said N represents the number of compounding periods. How many times interest is calculated? Okay, if interest is compounded annually, it's only calculated once a year. If it's compounded monthly, it's calculated 12 times a year. If it's daily, it's calculated 365 times a year. Every day, new interest is calculated. So let's keep things simple. Imagine you've got $1 in a bank account and the interest rate is 100% per year. Okay? What is going to be the value of your $1 investment if interest is calculated annually? Well, it would be A equals 1, because that's our investment. 1 plus, well, 100, how do we write 100% as a decimal? No, 100% is a decimal. 1. And number of compounding periods? 1 annually. Raised to the 1 times 1 again. So what does this give us? 1 plus 1 over 1 is 2. 2 to the 1 is 2. 2 times 1, which makes sense. Because if you earn 100% interest and you've got $1 in there, you get a whole another $1 at the end of the year, right? Let's go back to the beginning of the year and say, okay, this time it's calculated twice a year. So the only thing that changes in here is N. So A is going to be 1 times 1 plus 1 over 2 raised to the 2 times 1. N becomes 2 instead of 1. If you were to calculate that, obviously you're going to make more money because interest is calculated an extra time. So you get 225. What about quarterly? 4 times a year. Well, this is going to be bigger, and it works out to approximately $2.44 is the value of your $1 investment after a year. Oh, sorry, yes. Now, I'm not going to keep writing this, but I'm just going to show you if we did monthly and it's 12, okay, we would get approximately $2.61. Daily and it's 365. Well, now we're getting very, very precise estimates. So I'm going to go beyond 2 decimal places to say it's $2.71, but then also this amount. 2.71457. Notice it keeps climbing, but how much it climbs slows down. Like here it's 25 cents, here it's 19 cents, here it's 17 cents, here it's 10 cents. It's still going up, but it's slowing down how much it's going up. And it really starts to slow down when we do this. Because hourly, well, how many hours are in a year? You'd have to do 365 times 24 times 60. I don't think so. I think it's bigger than that. Isn't it?
I thought it was.
525,600? 365 days times 24.
Oh,
So it's 24 hours in a day. So no, it'd just be three. Yeah, it would be 365 times 24.
yeah, it could be 8,000.
Sorry,
8,000.
8,760.
Yeah. This is per minute.
Yes, that's per minute. Thank you.
So,
Okay, 525,600 per minute. So no, it starts to slow down even more. So here we get 2.71813 per minute. We get 2.71828. Now it's getting really precise. Notice that it's approaching a number. And this number that it looks like approaching is about 2.718. If we did it continuously, those of you in intro, we would want to find the limit as n approaches infinity. So as n keeps getting bigger and bigger and bigger and bigger, our formula is going to look like this. A equals 1 plus 1 over n to the n. It's going to approach this number. So if you just continually calculated interest, it doesn't keep going up and up and up and up. It approaches a certain value. And this is the value that we call that it approaches. And because it's a number, we can do log stuff with it. Okay? Like I could find log base E of, oh, what's log base E of 1? No, won't help you. Don't do it. Don't do it. It's a non-calculator. Come on, you guys. You know how to change to exponent. E to the whatever this is equals 1. 0. Log base E of E. 1, because E to the 1 equals E. I could graph these. I could graph e to the x. What would e to the x look like? It would look like somewhere between 2 to the x and 3 to the x, right? So I can do different calculations with e. However, we don't write this So yeah, this is just, we can write e to the x and its inverse is log base e to the x. And a log that has base e, we call it a natural logarithm. And we write it like this, ln x. And ln is pronounced ln. And if you look on your calculator, you've got a ln button. It's usually above or beside, above or below the log button. So whenever you do a calculation involving logs of base e, you're doing a natural logarithm or a ln. So do this on your calculator now. Do ln of 1. You should get 0. Do ln e. You should be able to find the e character on your calculator. You should get 1. It should be somewhere on your calculator, just like the 5. You've got e to the x. Yeah, that doesn't work. Yeah, no, I don't. You may not be able to do that one. You able to do it? Oh, yeah. Button right there. Good. Yes. Well, yeah, because we did that. Okay. So we can use this type of log to solve problems that involve continuous growth or continuous decay. Substances continuously decay, many substances. Population continuously grows. So let's look at a couple of examples. So here we have a population of 500 bacteria. It grows at a continuous rate of 5%. Here's the formula we use that represents the amount of the bacteria is whatever we started with times the number E raised to the rate of growth times how many hours or the time, how many hours, how many days, how many years, depends on the question that you're given. So in this question, we are asked this. We're asked the population, so it's A, I don't know. What is the current population? 500. So capital T is 500. E is obviously 2.718. What's R as a decimal? 0.05. And what is the time we are looking for? 20. So use the formula 500 times E to the 0.05 times 20. Well, that's the same as 500E. What's 0.05 times 20? 1. Okay? So our answer is going to be 500 times E to the first. So you should have an E to the, I think you should have at least an E to the X function on your calculator. So do E to the first, it should work out to 2.718 something. And then times it by 500. And let's say, well, because it's bacteria, we'll nearest whole number. Do we actually know how to say it properly? Instead of just reading 1,359, thank you. No, we'll stop there. We'll just say 1,359 because it's bacteria, so. Yeah, well done. Okay. But what if we're trying to find the time? How long will it take the population to double? What's the amount of P again? So what would be the amount of A?
1,000.
1,000. R is still 0.05. T is what we're trying to find. So what does our formula look like? 1,000 equals 500 times e to the 0.05 t. Notice the unknowns in the exponent. That means we're going to have to do logs. But because it's e we're dealing with, we're going to do ln. Okay? First of all, I need to get this out of the exponent, right? I need to get the t out. Okay, but before I do that, let's get rid of this. Divide by 500. Divide by 500. So 2 equals e to the 0.05 t. What must I do that allows me to pull this in front? Take the ln of both sides. So ln 2 equals ln e to the 0.05 t. Now I can pull this in front. Ln 2 equals 0.05 t times ln e. Here's the nice thing about doing that. What is the ln of e?
1.
Always. So this is 1. So really, it just kind of disappears, doesn't it? Because this times 1 is just this. So this kind of just goes. So how do I get t by itself? What's the last step? Divide by 0.05. Divide by 0.05. And let's go, oh, it says to the nearest hour. So nearest whole number. A little faster next time.
Yeah, you
Disappointed. Do you notice that whenever I say something to Ava, she must always respond.
Listen, I know you're gonna.
She cannot take, I guess I'm talking about her in the third person, almost like she's talking about me. Okay? She.
Call your mom.
What? Oh, I don't even want to start. Okay, this one. Here's a continuous decay. How do I know it's decay? Because it's negative. Negative exponent means fraction. Fraction means getting smaller. So here, a radioactive substance is decaying according to that formula. If there are originally 80 grams of a substance, how much is left after 3 years? So what's A? Question mark. What's P?
80.
What's R?
No.
Actually, I don't even need to know R. There is no R in this one. Actually, R is negative 0.2. We're dropping 20%. What's T? T is 3. So, come on, you guys. So we have to do this. What is negative 0.2 times 3?
Negative 0.
Okay, so on your calculator, e to the negative 0.6 times 80, that should result in a smaller number than 80. What do you get?
44.
44?
Grams.
44 grams. Good. Okay. So that's where you just plug in calculator. What about if we're asked to solve an equation? So this time, P is still 80. P is 3. If we are looking for the half-life of a substance, how much would A be? 40, right? Because it's the half of whatever we started with. That's how you find half-life amount. So we would do 40 equals 80 times E. Oh, sorry, T is the unknown here. To the negative 0.2 T. What do you want to do first? Divide 80. Divide 80, so we get 0.5 is equal to E to the negative 0.2 T. Log both sides, which allows you to use one of the log laws to pull the exponent down or to pull the unknown down from the exponent. So we get log 0.5 equals negative 0.2 T ln E. Remember, whenever you see ln E, it's basically the same as times 1, which means it's just disappears. So we divide by negative 0.2 to get our T. And what's the half-life of this substance? 3.5? 3.5 years. Okay. So you see, we do them in a similar way that we did the log problems earlier on in this exercise. Okay, but like don't get thrown. If you see on the provincial exam or on some sort of assessment, don't get thrown by E, just remember the value of E. It's 2.718, right? So, and if you can't remember the value of E, just do E to the first on your calculator. You should all have an E to the X side. Just do E to the first and you'll get the number. 3.5 years. Okay. It's not